So there are a few things that I need to tell before starting. That when you write homeworks, first thing, do not copy paste, because that's a very bad thing. And when you write the homeworks, try to explain yourself as much as possible, because till now I saw the homework, there are 5 people who have submitted, and I just look at what they have submitted, and 1 or 2 people they have submitted, they do not explain anything. They are like, this is the question and this is the answer. Now it's my job to interpret how did you get the answer. I'm not going to do that. You need to explain yourself, how did you get that answer. If you do a kind of a, there's a 5th question in the homework where you see the contraction of the indices. You need to show me that you have done the contraction of indices. You are just like, okay, this is the question and this is the end of the answer. Now you go derive yourself, how is the contraction done. That is not good. And one more thing that I think first thing is that you should start writing in LaTeX, because out of 5 people, 2 people are writing in the language which I don't understand. Language in the sense it's in English, but the way it is written, it's very difficult for me to interpret what is written. So if you write in LaTeX format, it will be very easy for me to read. And okay, and anything more? Yes. I'll write my email if you need. I think you already have access to that from the Moodle, but I still will write it. This is the regular one, or you can also the one which is on the syllabus. I think, if I'm not right, I don't know. Okay. Yeah, one more thing. Since I'm also not a native English speaker, if you think that my English is not good enough, or you find that it's difficult to understand anything, you can tell me. So this is my email if anybody needs it. And anyway, I'm here in 512, room number 512, if you have anything to ask. Okay, so let's start. Writing is not that bad. Hopefully you can understand. Okay, so let's start with, I'll erase this. Nobody is nothing it down, right? Okay, I'll erase this. Okay, so we'll start with the Maxwell's equation. If you saw the lecture notes of Asaf, in the special relativity chapter, at the very end there's a Maxwell's equation, the covariant derivative of Maxwell's equation, that I'll derive. And if you think that I'm speaking too fast also, then also you can tell me. Means if you have any problem, tell me before, I go too fast, or I said at the end and then realize at the end, I didn't get anything what you said. So it's better from the beginning. Okay, so let's start with the Maxwell's equation. Okay, so you have seen Maxwell's equation, right?
Yes, yes.
Okay, good. So I'll start with the continuity equation. And I have bad habit of not writing the vectors, so please bear with me, but you are supposed to write it in the vector form. This is the continuity equation that you may have seen for the flow of a fluid. Like if I have a parcel of a fluid, the fluid is flowing from this side and coming out of this side. This is a kind of a surface of the area of the pipe in which the fluid is flowing, and I'm looking at it. So the amount of fluid that is flowing through in here is the same as the divergence of the, it's fine. So I think you already have seen these things.
Yes.
So this is the continuity equation, which says that the amount of fluid that flows from one point in any flow is the same as the amount of the flow that is coming out from that surface. So what goes inside, that is the same as what comes out from the surface. And we have this thing, and multiply this by charge. You have, if you have NQ, which we define as density, right? And then when I multiply Q in here, it will be NQV, which is rho times V. This is we call as a current density. Okay. So with this, I can write the continuity equation for the conservation of charges. That will be we also call it as a J. This is the continuity equation for the charges. I think Asaf has already shown it in one of the previous classes. That's fine?
Yes, yes.
Okay. Here also is the same thing. The amount of charge flowing from one side of the wire is exactly same as the amount that flows outside. Okay. If it is too basic, and you can tell me. I'll go fast to the something that is more important. Okay. So let's write down the Maxwell's equation. First, I'll write down the Maxwell's equation the way you know it. Which book, by the way, you studied the electromagnetism? Griffiths? Jackson? Griffiths. Okay, so this is equation, by the way.
Okay.
This is what you derive in. So this is the, which law it is? Gauss law. This one is?
No.
It is. Okay, there's no magnetic monopole. It doesn't have any specific name, but people sometimes do call it Gauss law for magnetism, but it's not. Anyway, this says that there is no magnetic monopole existing. This one? Faraday's law. Ampere's law. Okay, good. So I'll write down the same laws in little bit different notation, not very much, because the way it is written in the Asaf note is little different than what I'm writing in here. So it's if I miss the sign of vector anywhere, you know that it is a vector. You have to be aware that maybe I don't have habit of writing the vectors, but it is a vector. Okay. So these are the four Maxwell's equations. So there's nothing different in here and here. See? The only thing that I included in here, this is the most basic form that you study in the, I don't know, first year, second year in the electromagnetism course. It's the same thing in here. This is the same as the Ampere's law written. Here I have used the 4 current vector. So this is J. Write it here. That is defined as rho C J 3 vector. You have seen this as well, hopefully. It is there, right? Okay, this is the way you write it in the 4 vector notation, and this is the form of the current density vector. This is the first component, second, third and fourth component. Okay, so what I will do now is I'll write these Maxwell's equation in a little, because now if you look at this Maxwell's equation, you don't know whether they are invariant or not, because I mean, why did we start studying the special relativity, or why did Einstein came up with the idea of special relativity? Because earlier the Galilean transformation didn't work, so he had to come up with something that works with the Maxwell's equation. So if you look at if you apply these Maxwell's equation in the Galilean transformation, they do not work. That is why everything actually started in here, that why did we need to include the special relativity, general relativity and stuff. So these laws are not invariant in the Galilean transformation. We need to find out some other transformation where it works. So Einstein came up with the special relativistic Lorentz transformation where it does work. But if you look at the current form of the equations they are written, you don't know if they are invariant or not. So what we'll try to do now is to write it in the form that you can easily interpret that, okay, they are invariant. So what I'll try to do now is to change the equations into the form where you can see they are like written in the tensor notation, so that when it comes to changing from one frame of reference to another frame of reference, you can just contract the indices and raise or lower the indices, and you can change from one frame of reference to another frame of reference. Okay, so this is the main goal we are trying to attain in here. Okay, so I can write the entire board, right? It will be visible over camera. Okay. Fine. So let's start writing it in the form which can be interpreted. If you find there is any mistake, you can tell me. So because I haven't made notes myself, I might also make any mistake. So it's fine. Okay. So what is epsilon ijk? Levi-Civita. Okay. You are, as I've already defined it, Levi-Civita, the 4 Levi-Civita, alpha, beta, gamma, delta 1. So Levi-Civita, it is 1, minus 1, 0. And when it is 1, then you have even permutation of the, like ijk, jki, kij. If this is the kind of permutation, you get the positive one. If it is anything not in the cyclic permutation, then you will get the minus 1. Okay, and if any of the two indices are the same, then it is 0. Okay, so that's how you define the Levi-Civita. I mean, you already learned that how is Levi-Civita defined. So let's check it out. The way that I have defined, I have written this equation. So it's written exactly in this form. So the first equation corresponds to this first equation and so on. Okay. So now if you look at this equation, the divergence of B, it doesn't look anywhere close to divergence of B. So I'll try to somehow convince you that this is divergence of B. Okay. So let's take one of the example of the first equation, let's say. Okay. So we have to, I mean, this is what I'll try to prove that, of course, because that's what I have written in here, that this is del cross by the divergence of B. I can write it in the Levi-Civita as this form. Let's take the component of Levi-Civita. Let's say I equals to 1. So for I equals to 1, so it will be del cross B 1. By 1, I mean the x component. Epsilon 1 j k. Okay, so I already anything else? So I'll just I'll use Levi-Civita now and write out the first of the components. So this is 1. This is not I, by the way. Okay. Epsilon 1 j k is not equals to, when this thing will not be equals to 0. You have 3 components. Let's say I j k can take the value 1, 2, 3, right? So if I put, let's say, j equals to 1, 0. J equals to 2. So the only indices for which epsilon I j k that the Levi-Civita will survive, it will not be equals to 0 is for the following one. When j k will be either equals to 2, 3 and 3, 2. Okay. So this is fine, right? Just try to put each and every indices and try to check it out whether it's same or not. Just put these things in here. What is 1, 3, 2? Minus 1. What is this one? Plus 1. So it's you have it. This is the divergence, right? It's one of the component. It's written as, okay. Let's say 2 is uy and 3 is z. So this is d this is what you have. So that means I can write this as equals to that. Okay, everything else I have mentioned, it's the same thing. There's nothing I have changed in here. Okay, so only thing that I included in here is the epsilon I j k using the Levi-Civita, which I can prove that I can write the Levi-Civita. If I include Levi-Civita, I can include the divergence as this. Okay, go ahead.
This is still not looking at D and E and everything else as.
No, I'll go ahead. I have to. So I'll still, it's not written in the tensor form. I'll still include something at the end. Then, so because our ultimate goal is to write the first 2 equations as this. If I'm not wrong, yes. So the first 2 equations I'll write like this. So for that, therefore,
is there a reason for your choice of upper indices for epsilon and lower indices for the derivatives? Or could this be the same thing?
Where?
You wrote epsilon with the Levitz-Civita
Yes.
table with upper indices. And
No, no. You just need to know how to contract stuff.
Okay.
If you know how to do contraction, you can keep the things down and keep that thing up. Doesn't matter anyway. The contraction works the fine way. So if I'm not wrong, Levi-Civita epsilon ijk is minus of epsilon ijk. Maybe I'm not exactly sure, but this is how it is. So if you take the indices down, I hope I'm not wrong. So this is the way you can do it. So it's the same thing. You just take the indices down, and the contractions would be proper. You cannot write like this one.
Yeah.
No. Okay. So this is fine. I'll erase this.
You do the contraction with the metric tensor?
Yes. Yeah.
Spatial metric. This is a
Spatial one. Yes, of course. The spatial one.
with no timings.
No time indices. Because
this
anyway,
is-
I'm including I, J, K. That these are the Latin indices, right?
Hmm?
Alpha, beta, gamma is the Greek indices.
Yeah.
Yes.
Okay, so this is the Latin indices.
Yeah.
Okay. So this is the only spatial component.
Yes.
Am I the only one who is feeling really hot in here? It's anyway. Okay, so I'll erase this one. Let's go ahead and now. Okay, so we'll define a tensor, a second order antisymmetric tensor, which is called electromagnetic field strength tensor F mu nu. I don't know how much you have studied in electromagnetism, but if you have studied, you know how to derive this thing. You have not?
You haven't seen this in electromagnetism.
Some of us have seen it with Asaf.
Oh, you have studied with Asaf this semester? F mu nu.
Some of us.
Some of us.
So you know this thing? No.
Some of us.
Some of us did
Some-
another
some
course
don't.
that is showed in
Can you
the
repeat
other
it?
course.
Oh, the
Okay.
elementary particle courses.
Yeah.
Okay.
Not everybody.
No, so I would say
took the elementary particle.
no. I'm not saying that everybody took. I'm saying that he taught in the elementary particle, right?
Yes.
No. So the most basic, the most convenient place that you will find this thing derived or defined anywhere is the electromagnetism course. If you have not done it, or if it was not derived,
It was not
I think
It was not derived.
Okay. I'll write down and I'll try to somehow convince you that it can be derived from because I have not made the notes of it, but I'll still try to convince you that this can be derived from the electromagnetism. So this has form and this is an antisymmetric tensor. Okay. If you don't know how does it derive, so if you know this, I don't know, I don't think you know this equation as well. Have you seen this equation? Where here A is a vector potential, you define as phi A. Unfortunately, I cannot derive it in here, but this, so it's not like I am deciding an arbitrary strength vector. This can be derived. So this is a proper quantity which has been derived. So I am using this vector and I'll try to include this in here and somehow write my equations in the tensorial notation with including this electromagnetic stress and electromagnetic field strength tensor. Okay. Actually, I should have written it somewhere on side because I need this too many times.
Sure.
Yes.
Where should the minus of the V1 should be?
Oh. Which one you mean? This
For the
one?
V1, for the V1 inside the tensor.
Yes.
Which one of them are with the minus?
Oh, so these are minus signs.
Yes, but for V1, the only positive, which is not antisymmetric. So one of them should be negative.
I don't know if I'm not. I hope I'm not wrong, but this is how it is defined.
In the lower V1, you have a plus. I think it's supposed to be a minus. That's the,
This one?
yeah.
This is minus.
Okay.
Okay.
So now it's okay.
That's okay. So yeah, my minus, and so sometimes you will find it difficult to understand the minus and equal to, because my equal to is somewhere like this, and sometimes it's that small that you won't even understand that's equal to. So try to understand that. That's a, yeah. I know it's difficult. Okay. Good to point it out. Okay. So we'll try to make some notations in here as this. Oops. Ij is equals to epsilon ij k dk. I try to include these two things in here and get my Maxwell's equation into the form where I can use this stress energy tensor. If you want me to prove this, I can prove at the end, but for now, since I am going very slow, if I'll see at the time, so I'll not prove it right now. If you need, I can prove at the end. So I can anyway prove one of this. In here I have already, so I can write F mu nu as this is fine. Contraction rho sigma rho sigma. Okay, it's the same thing. Let's take the example of F01. It will be eta 0 0 eta 1 1 F 0 1. This I won't prove because now you know eta. The form of eta you know, right? -1 1 1 1. Everything else 0. Just try to put things in here and you'll get the even. Okay? And the same thing goes for here. This is bit tricky to prove, but okay. So now including these two things in here, let's write down those two equations. And what are those two equations? It will be I included these two in here. This is my first equation. This is my second equation. This one. Because you know this is the first component. Okay. I made a mistake somewhere. No. Okay. I mean, I'm getting very quiet response all the time I ask something.
It's the zero.
Either, sorry.
In the second equation, shouldn't it be dou I?
No, because this is the zeroth component. This is the zeroth component of J, which is the row.
No, on the left side, in the dot, in the partial derivative. Since f0i is di, so it should be di.
Di, right? Yeah. Okay, I need to verify this, but okay, yeah, because this is the. Okay, I might taking this. Fine.
Can you get something dependent on J, no? If you do I, F, I, J. Is summing all over the I's?
Yes.
Something depending on J. You don't know what J is. Get rid of J.
So you mean that this 0 was right there? Yeah?
No.
What do you mean?
No, I'm there.
The upper one?
It's doji.
Ah, okay. Never mind.
It's fine?
Yes.
Okay. So I can combine these two in here and I can write it this way. Four pi j mig. Okay.
The mu be the lower
On the left.
lower size.
The dot.
Good. Thank you.
No, something
And it's
You-
supposed to
no,
be a
it's really
mu.
J nu, not J mu.
That's my bad. Yes. D mu f. Okay. Now this is fine. Okay. So what I'm going to do now is to prove that this is from this you can derive those two equations. So we'll go the reverse way and say so that these two from this equation you can definitely get those two equations. So because what is the usefulness of this equation here? You have written this in the form of tensor, the electromagnetic stress tensor. If I go to another frame of reference, I can just simply switch over the indices and I can get the stress energy tensor and the Maxwell's equation into the another frame of reference. So it's very easy and convenient for me to do the transformation from one frame of reference to another frame of reference. That is the reason we are writing it this way. Is something wrong?
Shouldn't it be F nu nu instead of F mu nu on the LLN?
Go ahead. Good. Yeah, that's also fine. Or I can also write it like this way. Let's write it. If I write it in new, then I can write it as like, okay, yeah, you are right. That I can write it. This or this, both of this.
It's the new in the end.
This one is the new. Okay, so this is, yeah, my new is kind of a V, but okay. So yeah, you can write either this way or this way. Okay. So now we'll use this equation or either of these two equations so that we can get the Maxwell's equation from in here. So which one I use? The first one I use. Okay. D mu f nu equals 4 pi j mu. Put nu is equals to I. Okay, I start from this one. Just a second, sorry. I use this one. This one, right? Okay. 4 pi j mu. I'm writing it this way because you already saw that there is problems are every time. If I write the indices in the other way, there is going to be huge confusion. So
Yes.
I'll stick with the way which I have written so that I won't make any mistake. Let's say mu is equals to 0. Okay. And okay, this thing can also be written as this if you, this and these are same. You know that, right? You already haven't seen this notation.
Yes.
Okay, so let's put it this way. Both are equivalent. Put mu is equals to 0, so f mu nu 4 pi z 0. Now let's put, since mu is put nu is equals to all four indices 0, 1, 2, 3. So it's f0 1, sorry 0 0 0, f0 0 1 1 plus f0 2 2, f0 3 3 4 pi, j0 is row, right? What is f0 0?
0.
What is f0 1?
E1
Even.
minus
Minus even.
no, E1 because in there you wrote with lower.
I know it's here.
Okay, this is how I have defined it. D by D by 1, let's say x component, right? D by d1 of E1, that is x component. Okay, same thing, d by dy of EY. What is this?
Just
Okay, this is fine.
yes.
Same way you can derive the second one. This one. It is bit more tricky compared to this because this was the easy one. That's why I did it. I mean, I have done the second one as well, but this one was the easiest to solve. Okay, so there's no cheating going on in here. That's what I have to say.
How do you derive the other two representations?
Going to do it now. Because up to now, what I have used is this one only. I have not used this one. Right here you see I have only used this one. I'll use this one now. In the first equation I only use this assumption which I made. Okay, so good. Fine. The other two equation actually is not derived, but it can be derived in the same form. I'll write down the equation. I'll not derive the equation. I'll write down the final equation, how it is done, and then from that equation I'll try to prove you that this is not done the wrong way. So the way that you have to do is you do exactly the similar kind of a contraction of the indices that we have done in here, but I'm going to write down the final equation, that what is the other two equation for that. Where is the first? These are the first two equation. I'll write down the third and fourth equation, and they can be written in the form like, where is that thing? If I'm making any mistake somewhere in indices, please. Oops. Let me know. So the other two equations can be written in this format. And what is this bracket sign in here? It says that there is an anti-symmetrization of the indices in here. So the longer form of writing this equation would be this. So I can write the same equation as this. It would be f mu lambda f mu lambda plus f lambda mu equals to 0. Okay. What I did is just cyclic permutation. If you do anything, means if there is any other tensor where you have things written like this, if you do the cyclic permutation, you will have the positive signs. The moment you will do the odd permutations, you will have the negative signs. What happened? Okay.
What's that fixed? All of these indices are fixed.
Sorry?
All of these indices are dummy indices, they're fixed.
They are fixed ones, yes.
Okay.
So, is anybody have any problem?
So we have 4 to the power of 3 equations.
Actually, no. Some are. Because, okay, so this is all dependent upon the f mu nu. So it has the sum of the components 0. So if you try to put those means this f mu nu in there, you will get most of them, I would say 0. So let's say now we have this equation, okay, and I can do the same thing that I did for that equation. That this equation, from this equation I can derive the either of them, okay. So this one would be easy for me, so I'll do this one, okay. I would say let's derive this one. This is the more kind of a difficult one. So I mean I have derived both, but
Actually,
yes.
it's supposed to be more long stuff. That bracket is on all 3 indices.
Yes.
That's supposed to be all the permutation with the right signs divide by 6, something
Yes. So
more complicated. That is
okay. If you see the Asaf's notes, that's what things in here. I'll show you exactly what he has in his notes. I did not print that thing in here, but yeah, exactly. So that thing is, if I write this equation, like let's say I have any tensor of the mu rho sigma, then I can write it as 1/6 T mu rho sigma minus T mu rho nu sigma plus T rho mu sigma. This would be plus, right? Rho mu, yeah. It's a very long
6 terms.
Yeah. T mu rho sigma plus T nu rho mu sigma minus T
Because
rho.
of the antisymmetry, it's equivalent to what you wrote.
Yeah, exactly. So I did not want to write this thing whole. That's why I said that because of the antisymmetry of this thing, that bracket stuff, that you can write this equation as this one.
And you also multiply by 3 because...
Yes.
Okay.
Because here you see that 1/6 term is there. Okay, so these are the whole 6 terms, if I'm not wrong, mu no sigma. Okay, so this is the form you can write for any tensor. For the even permutation, you will have the positive sign. For the odd, you will have the negative sign. And I have used the same thing in here. Because of it's the anti-symmetrization of this bracket, indices in the bracket, I can write this equation in here as this one. Okay, it's fine. Now the people are more quiet, so I don't know whether I'm going wrong or
No, you're fine.
you don't want to ask some stuff. Okay. So let's try to derive this equation from in here, so that we know that this is not wrong. Let's we'll start with, let's put mu equals to 0, mu equals to I, and lambda equals to j. Okay, we'll put in here 0 I j plus I j 0 plus f j 0 I. This is fine. Okay. Good. I'll use this one. So f 0 I will be minus of e I, and f I j will be epsilon I j k b. I'll try to use these two, which I have already somewhere there. Okay. Here I just pull the indices down, so I wrote it in negative. Okay, and this is exactly the same thing. Okay, fine. So let's put this thing in the equation. Fine. So f0I would be, so this is minus of ei. I'll write it this way, j ei plus epsilon I j k I'm trying to write this one by d0 b k plus fc0 would be minus of, no, this is f0I is minus of, this will be plus d I dj. Does this make sense? Hopefully it should. Minus 0I, where have I written? I erased that? No, it's this one. Okay? And if you see in here, it's a 0I, J0. So here I switch the indices. So there isn't, here it's a negative sign, but here it is not, because they should have the opposite signs. It's fine?
Yes.
Any difficulty? No. And I wrote this equation as this. Something to ask?
Can you explain the next term?
So, okay, this one I put by that use thing that I have written. So I have 0I, since here I have the upper indices, I pull it down, I wrote it in negative. And Fij, it's the same thing as written there. Okay? What I did is F0I is minus EI, and J is here. So it's the same thing. Okay. For Fij, what I did is I wrote it in the form of the Levi-Civita. Here K is my dummy index, contracting, you have Ij. It's fine. And I am taking the time derivative, sorry, the derivative with the 0 components with its 0 component I have written in here. Fine. And the same thing in here, but here the indices are switched. It's not 0I or 0J, it's J0. So I have switched the sign to positive. Fine. But what is this term in here? So I'll write, sorry. Does this sound familiar?
Yes, it's Faraday's law.
This is Faraday's law, right? Oh, it's visible right from there.
Yes.
So how I can write it as del cross E, which is this term, and plus
What two equations are given by this big equation?
this one. The second and third. The first and second are d nu f nu nu 4 pi j nu. Yeah. These two are this, and the second ones are this one. Okay. So from this equation, we can prove that we can get the Faraday's law. Okay, that's fine. Okay. So we are done with this. From this f mu nu, okay. I will erase some of the stuff from here. Okay. So you with okay. Go ahead.
Just a question.
Yes.
How did we get rid of the Levi-Civita?
Okay. So actually, we get I erase the Levi-Civita again. So I can get rid of Levi-Civita. I mean, you can get this equation only if you put the right indices of the Levi-Civita. What I mean by that is, okay, how should I tell? It's like the problem here is I am trying to show it in the form of ijk. So let's put ijk is equals to xyz comp. Sorry, yes, ij and k comp. This is k should be, yeah. So let's put ijk equals to xyz and try to put in here. The only point when you will have this thing surviving when your B will be, sorry, when your Levi-Civita will be either 1, 2, 3, 3, 2, 1, sorry, or 3, 2, 1, or 2, 3, 1. So by this, it's not only a single component, you'll have three components. So here it will be Bx, By and Bz. You have all three components of the B. Okay? By this, you can derive all the three components. Here, all the three components are there. I'm not so that's what I'm saying, that you can take the I, J and K as all the three components at X, Y and Z, and you can derive for all the three components of the magnetic field and electric field vector. Am I clear now? Because if I take only one of the component, I will derive only one of the component of it. So it will be like del cross B, sorry, dBx over dt, and this will be the, let's say, d2 d2 ei, so d2 e1 plus d1 e2, and this is, let's say, 1. By 1, 2, 3, what I mean is x, y and z component. Okay, so put the value of I, J, K as x, y, z, or 1, 2, 3, whichever you like, and then you can derive all the three components. Fine. We have time. I need this now. if something is not clear, you can ask me, or you can come to my office also ask me. Don't be quiet, because I also don't know whether you understand or not, and I don't know what I'm saying. So anyway, it's good for both of us to know if I'm saying something which makes sense for you and you understand that.
Everything is clear now.
Okay, so what I'm going to do now is to use this F mu nu. I'll write it somewhere here now. Do I need it? I'll write it later. So I'll use the F mu nu that I have defined, and I'll do the transformation of electric and electromagnetic fields. Like if I know the electric and magnetic field in one frame of reference, and get the the transformation of those electromagnetic fields into the other frame of reference. Okay, so let's. How many of you are math student here? Like really math student? Okay, so okay, there are very few. I thought there will be many more.
More tone.
Ah, okay. Always remember to keep a space between the upper indices and this upper index and this index, right? In exam, definitely don't write this. This is horribly wrong. I have alpha, beta, gamma and alpha, beta, gamma. This does not make any sense, right? There should be space between this. So if you have a very large tensor, your next alpha should start from here. I think it has already been emphasized by Asaf.
Yes.
So don't write it like exactly over top of one top of the other. Okay. For simplicity, what I can do is to take the instead of alpha, beta, j, gamma, I can take ij. So that is not going to change anything for you, but it's the same thing written here. But you see, the summation is done over K and L. Okay?
But the Latin letter should be only from 1 to 3 without the zero component. That is what
Yes, so okay. I mean, that's why I said for simplicity, let's consider IJK. This is it has the same form as this. So for simplicity, I'm trying to take Ij components. You have the zeroth component of electric and magnetic field also transforming to the other field if you go. It's not like the only, okay? I think, yes. Okay. So what we can do is for the transformation of the matrices, for the transformation of electromagnetic field is I can do a direct multiplication. I can do is lambda and do the transformation, okay? But if I do it this way, those who can really, okay, I'll write it down, then you will realize what is going wrong with this. Do you see something not being right in here? Indexes. So if I do the direct multiplication to transform, I'm summing over the indices which are not the indices which I want to sum it over. So I'm doing the multiplication wrong way. Okay? Is this clear? So I mean, this should be very. It's fine or not? I don't know.
It's fine.
Okay. Okay. So this is the problem in here. Here you see that you have to sum it over k and l. Here I am summing it over I and k. The thing is, we cannot sum it over this way. So we cannot do the direct multiplication and get the transformation. We need to somehow, what can we do to make this thing work?
You multiply once from the right direction to the left.
Yes, exactly. And when you multiply from the right, you need to take the transpose of it, because you need to make sure the indices are done the proper way. Okay, so I'll write it down. So let's do this thing first. Okay, first I'll make the sum of lambda and f, which will be my k this is fine. Now what we have to do is to sum over L, not I. Okay, to sum over L, what I will do is to multiply this thing with lambda from right. Okay, it's lambda. Okay, any problem? No. Okay, so what I have in here, I can do is to I need to take over the sum from for the lambda, which is lambda j l, this one, right? I will multiply it from the right hand side. This thing I'll multiply from right. Okay, and what will I get is, I'll show you how I can write it as lambda f lambda transpose. This is the actual way we can do it, but I'll show you how I can write this thing in here. Sorry, this one is this way. Okay, because this is the actual way. If you do the multiplication, you can get the transformation of the electromagnetic field. Here we are doing the summation over the wrong indices. So what I'm going to do is to, okay, k lambda I kappa f kappa l lambda j l transpose. Is this fine? I wrote this. So first what I did was to take this multiplication. I just wrote it in here, and then I multiply with the transpose here. And then the next one, what I did is just to take the transpose. It's okay?
Yes.
So here now we have our indices are right, because now first I sum over k and then I sum over L. Okay, fine. Now we have to do the brute force multiplication, which I won't do anyway. I'll write down the matrices and the answer, because those matrix multiplication was in first year. When was matrix multiplication? So we have to just multiply lambda gamma minus beta gamma gamma everything else. Sorry. This is not, okay, let me. Zero, 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 zero. Okay, this is my gamma, and the if you
shouldn't there be a 0, is it?
okay, it's fine. Yeah. And if you notice there is a lambda and lambda transpose are the same. So I write down F again F, okay. Then again I have to multiply it by the capital lambda here, okay? Because lambda and lambda transpose both are the same. Okay, go ahead.
If we have a spatial rotation, which is also a kind of transformation, lambda wouldn't be symmetric. So it would be maybe not be anti-symmetric. It would be a rotation transformation, which isn't symmetric.
So you mean you are talking about the rotation?
Yes.
So which then
This
in that
isn't
case,
it isn't a symmetric transformation. But it transforms the same way. We could multiply the same way.
yes.
Transfers.
So it's the same way you have to multiply it. There's nothing going to be changing in here.
But
Get the
lambda
matrix for it.
transpose will not be equal lambda.
Yes.
Yes, but well, okay. In here it is equal. That's what I'm saying. It doesn't need to be equal for you to multiply. There's no necessity that these need to be equal. Okay, so do the brute force multiplication in here, and you will get even prime. So because here I'm writing in the prime with the prime indices because I'm trying to transform it. So here I'm showing that it is in the another frame of reference. Okay, so even prime will be even, b1 prime will be b1, I'm sorry for my writing, so you might also have confusion between beta and B. So hopefully you should not have it. Okay, so this is how you get the electromagnetic field getting transformed from one frame of reference to another frame of reference. So if you look at the another frame of reference, then the given then you will have the transformation of electromagnetic fields, like the electric and magnetic field, the components of the electric and magnetic field, I would say. Each and every component transforms. Okay.
How about the electromagnetic potential? If it's just a regular vector, it transforms like a regular vector.
I am not exactly sure, but it should. Yes, I'll check it out. Yeah. Okay. anything in here to add. It's fine. Okay, so I have some silly problems which I decided to solve. I still have enough time, so we can go over them. There is a very easy problem for people who know maths. Prove that Kronecker delta is a tensor. It's a very easy thing to. What we have to do is to prove that the Kronecker delta is a tensor.
You put Lorentz and Kronecker delta and the Lorentz transpose.
You don't need to. So
No,
what?
you don't need to.
No. So how you can prove is that you can simply multiply with the two components of a vector, and if you get out of as a scalar, then you know that it transforms the.
If it's also multilinear.
Sorry.
It also has to be multilinear.
Yes. So how I can? Okay. So. Is tensor. The easiest way would be, what we can do is to multiply it with the component of the multiply it with the two components of a tensor. So what I can do is to take the any two vectors components, like let's say a nu, b mu, and multiply it with mu nu. What you get as an output in here? Sorry, it will be a dot b, and which is a scalar. So now you know that if I multiply the two components of a vector with a Kronecker delta, you get a scalar. This is a property of a second rank tensor. Okay. So you can use this, or okay, let's this way you can say that okay, it is a tensor. What is the another way of saying that it is a tensor? Let's do the coordinate transformation. So yeah, you were saying something.
Showing that it is multilinear method.
Okay, you can do that, but I mean, we are not going to do that in here because we try to interpret like in physically what does it mean. Mathematically you can do that, that's fine. Yeah, so let's do some kind of a transformation property. So let's say I have two vectors like this, 1 and x beta by 2x mu prime multiplied by, okay, this is just the transformation of the components of the two vectors that I have taken. You have studied the notations, right? I hope you do. And I can write this as is this fine?
Why
Does this
not new prime?
Oh, sorry, yeah, exactly.
Oh, okay.
That's. Does it need any explanation? It's fine. And but what is this equals to? So it does transform like a second order tensor. I speak something because I don't know whether the people, when I look at the people's faces, it feels like, okay, either everything is clear or something, I'm talking something which doesn't make any sense. This is fine, right? So it transforms like a second order tensor, or if I multiply it with the components of two tensor, I get a scalar. This proves that it is a tensor. Okay.
You need both to prove it's true?
No, it's the same. I'm just giving the and. You can show this as well. You can show this as well. I'm giving both the options. Like, okay, it can be proved this way. There are some other ways also to do that. Okay, this is.
That means that the first thing will mean that the second thing will also apply.
This also apply. Yes.
If I mean from the first thing you vote, you can get the second thing.
So from here you mean something like this here?
Yeah,
if you do the transformations. So
if you assume that a tensor will give you a scalar for vector inputs.
yes, but it will be. I mean, it can only be applied for the second rank tensor.
What if I can get it? For example, if I have two vectors for input for just a function, okay, and I will get a scalar from that function because it's 8 vectors and gives out the scalar.
Okay.
What is different than what you proved there? You still need to show that it's linear.
Yes. Yes. So in that case, this won't only be the condition which you can show that this is a tensor. Then in that case, this will not be the only necessary condition which you can show that this is a tensor. Then you'll have to do the transformations.
Okay, so I still
need to do the transformation exactly.
Okay.
So this is not. There will be the cases where this won't be the only necessary condition which can say that okay, this is a tensor. I'm trying to tell about the Kronecker delta in here as a.
Okay, it's just because in this case it's the dot
Yes.
product, so it will be invariant and all of that.
Yeah.
Okay.
Okay. There is another easy example. Oh yes. Also, does anybody of you have any problem with the homeworks? If you do, you can ask me. I mean, I won't give you the answer, the problem, but I can tell you how to do it. So I can give you the direction. Okay, this is how you can approach the problem.
I have a question.
Okay.
For question 6.
So I mean, I can
Later.
tell at the end. Yeah, exactly. After the class, we can.
Yes.
I mean, anyway, I'm here from something like 8:30 to 6:30 every day, just very close here in 512. So if you have any problem, then also you can come. Okay. Let's take the another example as I have a f alpha beta as a second rank tensor which is antisymmetric in the two indices, and I will ask. I mean, the question is to prove that f alpha beta is antisymmetric. Prove that f nu alpha nu alpha equals minus of f nu alpha beta f alpha beta. It's very easy, just needs to do some contractions. Okay, let's see how we can do it. We'll start from this one. Alpha is mu alpha beta alpha beta. Okay, I don't know why I decided to write like this, but here I'll just write fine. It's the same thing. I'll start from in here and do what? Let's see. Oh no. Yeah. It is fine. Sigma contracted, you get beta alpha.
Where did you write derivative on?
Sigma beta. Not
Sorry?
beta sigma.
Where?
Yeah.
This one?
Yes.
No, why do you want that? Because this is the first index in here.
Why did you write derivative on eta? Not on.
Oh, okay, so it's, I would say it's written like, it should be written something like this, if I'm not wrong. It should be written something like this. Okay? Oh, no, I did not include the one step in between. So is this fine? I'll write the middle step also. That's in here. I can write F mu nu beta F beta sigma eta Does this make sense?
Yes. Yes.
Okay. What will it give me? The same thing that I wrote.
Delta.
Yeah, exactly.
Sigma.
So this is F mu nu beta F beta sigma delta alpha sigma. Right. Fine. And you know the property of this.
It's not delta alpha sigma, delta mu sigma. I think it's summing over alpha.
What do you mean? Something wrong?
Wait, you're summing over alpha.
Oh no.
Yeah, summing over alpha there. So it's delta eta sigma. Or delta gamma sigma.
No, so I made some mistake somewhere. Wait.
Isn't like the from the first line to the second line?
Yes.
Is it supposed to be on the first line instead of gamma nu?
Gamma nu, where is that?
In the like the
This
second,
one?
yeah. Isn't
Okay.
it supposed to be a nu? So we can get the F nu alpha. No, nu.
Wait.
I think.
Sorry. Yeah, that's
Yeah.
that's a mistake. Yeah, exactly. This is not gamma. This is nu.
And so here it's supposed to be nu too, instead of alpha.
So here it should be. Is this fine?
I think.
Yeah. Okay. Sorry, that was my mistake. Yeah, because here nu get contracted, you get mu sigma, mu alpha, and here you get beta alpha. Fine? Okay. Now I already told you that it is antisymmetric, so I can write it as F instead of mu nu I can write as nu mu, right? Minus, sorry, yes. Beta f alpha beta.
Alpha, where is the alpha?
Oops.
New.
The alpha is
New
supposed to
beta.
be new. Yeah.
Oh no, so there shouldn't be a minus sign there. Because you flip the order of indices twice.
Which one?
You flip the order of indices once for the second tensor, once for the first
And the
tensor.
above should be
So it should be a sign change.
So it's f mu nu beta f beta sigma sigma. Okay. So it should be f nu nu.
Yes.
It should be plus
No, it's supposed to be a minus and mu nu.
mu
instead
nu.
of-
Yeah, exactly. Sorry, that's okay. Here's minus f mu nu. Sorry, that's fine. Okay. I have one more problem from spatial relativity. I hope you did this problem in spatial relativity in very first course. That it is impossible for an electron at rest to either emit a photon or absorb a photon. Did you do this problem?
No.
So if an electron is at the rest, it can neither absorb a photon or nor it can emit a photon.
Why is that?
Okay. It's 28. I still have some time. I erase that. An electron at rest cannot. By cannot, I mean it is impossible for an electron at rest to either absorb or emit a photon. Emit or absorb photon.
At rest.
Sorry, at
In any frame or.
yes, at rest. This
No,
is the most
in
important.
which
Yeah.
frame? Of like, like an observer who stands and sees the electron or.
No. So it's the me looking at the electron and saying that it cannot absorb.
No, yeah,
Absorb.
but if you go, like, if you walk, okay, and
Yes.
the electron is staying there, but you walk, the electron can't observe any photon still, right? Doesn't care about you. So which frame are we talking about?
I hope no. It does not. It does not.
What about the rest frame of the photon? Of the electron? If you're talking about the rest frame of the electron is always at rest. So it can't always emit a photon? Or the photon emission or absorption, does it depend on the reference frame?
It does not. I'll try to show you from the what I have derived in here. Then you will find that there is some very basic problem that arises which can tell you that it cannot happen because the
But like we're supposed to look at the problem in a certain frame, right? And if we are looking at a problem from the electron's frame, so it's always at rest. If we're looking at the problem from like
no,
an
from the observer's point of view, we are
so
looking
the
at
observer can just like walk and it sees the photon moves, so it's not at rest, and the photon, the electron still is not supposed to observe any photon, right?
yes.
So because the observer has no impact on the electron.
On the electrons. Yes.
So what frame of rest are we supposed to look at?
It's a good question, but I mean, it should not emit or absorb. But the problem is, I am not sure about in the other frame. So instead of giving the wrong answer, I will say I'll have to look at it, because yeah, this I need to check it out. That's a good thing. So everything in here. Okay, so let's look at the conservation of momentum. Conservation. This is TION. You people do this kind of stuff or no? Okay.
It's fine. It's fine.
An electron. I'll not make diagram because my diagrams are really very horrible. So, okay. This is the conservation of momentum, how I write it, because this is the momentum of the electron when photon is there. This is momentum of electron when photon is not there, and this is momentum of photon itself. Okay, and I'll write down the, so since the electron is at the rest, 0. So the momentum, the total momentum will be only the momentum of photon.
This is speaking in the spatial coordinates, right?
Yes.
What was the time coordinates?
For now, I mean, the way I have derived, I have not included the time component. I mean, it doesn't matter if you include the time component or not. The answer remains the same.
Okay.
So this is 0, right? Because the electron is at the rest. So then I can do the energy conservation. What I have in here is E prime is E plus E nu. Okay. It's a very basic, the first year special relativity way I am trying to do it. Not in the 4 notation or something that is going very weird. It's a kind of the easiest way I found that I can do this. Okay, so now we know what is E. This was already derived. Put in everywhere. Okay. Take the square of it. Will be, it's okay. It's square nu square c square get cancelled. I have now you should realize the problem. Look at the left and right hand side and tell me there's something like very much wrong. Is it possible? I won't put equal to sign that because that's a. Is it possible? M not 0. Or let's say photon is present, but does photon have 0 frequency? Does that thing make sense? That means photon is not even present there. There's no photon because the frequency. Or this needs to be 0 either, and this needs to be 0, or or nu equals to be 0. Then either of them would be 0. This 0, that means there is no photon. What does it mean? That there is no photon in here. Okay? So when the electron is at the rest, it doesn't feel anything. A photon is going, will just pass. Or neither it can emit the photon. Okay, go ahead.
Does it have to be in rest?
It does. It definitely needs to be had. That's why I made a bracket in here.
It can't work in
Electron.
assumptions?
Sorry.
It can't work for other assumptions. What would it do?
No, if the electron is at the moving, then it will emit the radiation. So
You have the moment, like the electron's moment, right?
you have the electron's moment. Then yeah.
If it's accelerated, you will have radiation.
Yes. Then you will have the radiation. Then
So it's for any inertial frame to the rest frame.
Yes. So the important point here is the rest frame.
Okay.
When the electron is at
Not
the rest.
any inertial frame.
Yes.
Okay.
If the electron is at the rest, it cannot. Okay.
The electron is always, as we said, the electron is always attractive to itself. So the electron can never emit a photon.
One photon, maybe
No.
2 or something.
The number of photons emitted shouldn't be a function of the observer. The observer sees all the photons moving at the same speed, just with different frequencies.
Yes.
No, but that's true for any inertial frame of reference.
Yes.
If that's true for one inertial frame of reference, that would be true for any inertial.
No, if it's true for one, then it is true for universe. It's like universally all inertial frame of reference.
So
There's no like a specific choice of frame of reference where it is working and where other places it won't work.
it is not depends on the inertial frame of reference. It's not depending on
It has to
the
be
observer.
Okay. So I still have one more problem, but I want to go over it. So if anybody needs help with the homework problems, I can help.
No? Short question.
Yeah, if you have anything from the lectures beforehand to ask, then also you can ask. If you don't have anything, you can ask about the homework problem or whatever that you feel is. Anything from previous lectures or something like up to special relativity, what we have studied now. Okay. So how was it? I was making sense when I say something. I was like,
Yes, everything was clear.
it's fine, right? Okay.
Right.
So that's why I'm asking like several times, because I need to know what I'm saying is fine, because next time I'll come the same way and start writing stuff and people are like, okay, then nobody is speaking anything, then I'll have impression that everybody understood anything, but well, I'll have the other understanding that people didn't understand anything the other way. So it's better to ask so that I can respond like things which I don't know, I'll go read and I can also answer that.
Short question. When will this next practice be? Because
Good. That I'm not sure.
Okay.
It's a very short semester, so I don't know, simply I would say, because Asaf has to teach so many other stuff, and it's I would ask you people, what do you think about the course? How do you like the course? Does it fascinate you or not? Because the funny thing about this course I found is like, this is the 75% of course. you will realize by the end of the semester, around end of the semester, just to derive this thing, you are doing all sorts of, this very small stuff is something like 60 to 75% of the syllabus. But this is written in the most basic form. Each of these has so many things. So this is the Einstein's equation actually. And this is, you will derive it at the, like, I would say, so for now, let that be the thing. Yeah. Cosmological constant and stuff, that is. And so this is the 75% of the course. This is the Einstein tensor, then you will have Ricci, Riemann, scalar, and all those things. Okay, now go ahead if anybody has anything to ask. I'm done with what I have to say.
Short question about question 6 in your homework. Do you have the
I have the, you want what?